thanks, Stuart, for the invite. Hello, everyone. I'm Tom. Nice to meet you. I wasn't sure what the crowd would be for today, but I think it's quite mixed. Just as a short question, who of you does any gait-related research? Small raise of hands. Okay, so that's, I'd say, about 25%, perhaps 20. That's good to know. Today I'm going to talk about actually most of the work I did. Like Stuart said, I did my PhD in Groningen on split belt stuff, and then I moved to Leuven for predictive simulation of walking. I decided to today talk about both because in that we are going from simple models, inverted pendulum models of walking, to complex models, and in the end we're going back to the simple models again. So I want to shed some light on the work, and who knows, we'll get a good discussion about that in the end. And my work is all about dynamic balance control in human walking. So let's see. There we go. So human walking is very adaptive. So when we walk around, we don't even have to think about where we place our foot, how we stay upright. And actually, that's quite amazing. We've gotten so good at it that we can now walk the streets holding our phone, texting our friends. I took the train here today, and I can assure you that more than half the people look at their phone instead of on the road, but no one walks into one another. And this is great. It gives us mobility. We can browse the world, explore it, go wherever we want. But if you think about it for a second, it's quite amazing. Because what we're doing is we're balancing a mass of about 70 kilograms on 2 legs, and while we're walking for most of the time on even 1 leg. If you look at this chair, I think you'd agree with me that it would fall over rather quickly. Luckily, we've got a musculoskeletal system, so we've got bones which make us rigid, and we've got muscles that allow us to produce forces and movement across the joints between our bones. And with the neuromuscular control, we can rely on this adaptive balance control. We can walk and do a lot of other things. It's not until we lose our walking function that we realize how important this is. This may occur at a somewhat younger age due to a sports injury, where you're temporarily immobilized due to pain or some other injury. But especially in aging or with disease, neurological diseases, you see that people lose their walking function, and this can affect their social life and their life in general a lot. So what we want to do is retain that walking function in aging, or restore the walking function after we lost it. And a lot of work has been done in that field in the whole world, but especially also in the Netherlands. We've come up with a lot of great devices. We've been able to speed up that rehabilitation process or the training process a bit. But there seems to be a bit of a stagnation in the treatment outcome. We're not able to burst through the ceiling and improve walking performance better in some of the patients after they lost their walking function. And a lot of what we do in gait training or rehabilitation is based on previous experience, and not so much on knowledge of the underlying mechanisms. So what you can wonder is, do we lack
to make the lives a bit more stable, because it's
this is
better to have
this is better. Yeah.
It's really
save me from an
and I'm looking at Dina that I should probably say more of this.
So what you can wonder is whether we lack knowledge of the underlying mechanisms of adaptive control of walking balance, or at least that's what I think. So in my work, I focus on which mechanisms underlie adaptive control of dynamic balance in human walking. And I think if we gain this knowledge and use that to inspire our training strategies or rehabilitation strategies or technology, we'll be able to burst through that ceiling and improve the walking function for patients or older adults. So here's a short overview of what I'll discuss today. The first bit will be my PhD work on adaptive control of dynamic balance. Then there's a focus on some of the work we did with USC and Radboud on balance control in stroke and Parkinson's disease. And the last part is my postdoc work from KU Leuven, where we develop predictive simulations of walking balance after stroke. So like I said, today I'll discuss the spectrum from simple to complex models of walking. And my PhD work was based on a very simple model of walking, the inverted pendulum model. So according to this model, you can model the walking human as an inverted pendulum, a stick that represents the stance leg over here, And we have the body center of mass on top of that pendulum. And you can model walking like a series of falling motions of the pendulum. And with each new step, we initiate a new falling motion of that pendulum. Now, based on that model and some of the work by Pai and Patton and Huff, we know that in controlling our balance, we're not just a falling pendulum. We know that we need some active control, especially in the mediolateral direction. And they came up with the theoretical framework of the extrapolated center of mass. Now, according to this framework, we can produce stable walking, so where to place our feet with respect to the center of mass, but not only taking the center of mass position projected at A into account, but also taking its velocity into account. So we have to take into account what the velocity of our center of mass is. And with that, we can calculate an extrapolated center of mass, which contains this position, velocity, and the pendulum eigenfrequency of the stance lag, or the characteristics of the lag. And we get a projection, a sort of dynamic projection of the center of mass shown at B. And as long as we keep that within our base of support, so where we place our feet at C, we produce stable gait. It's a very simple rule for stable walking. And we use this model to study walking balance. We can quantify this by taking this extrapolated center of mass position at B and the distance to the edge of the base of support at C, and we call it the margin of stability. We can change this margin a bit. We can make it larger by, for instance, increasing our step width, which you could say would be safer. We have a large margin between our extrapolated center of mass and base of support, but research has shown that this is less energy efficient. Or we have a small margin of stability, which is more efficient but less safe. And on top of that, because that's all about foot placement, or at least until you start the inverted pendulum phase. So when you stand on one leg, we look at the mediolateral foot roll-off. So during the stance phase, while you're standing on that inverted pendulum, while you're standing on that leg, you can actually use some of the ankle strategy, as it's also called, or inversion or eversion of the foot, to change the center of pressure under your foot and correct your margin of stability, for instance, if it was too small. We were going to study dynamic balance during walking. We did that with the margin of stability, which describes center of mass movement and foot placement. We look at foot inversion and eversion, or the ankle strategy, to adjust that margin of stability during stance. And more interestingly, based on some of the work by Henrik Reimann, who was here before, I think, we looked at these two mechanisms in relation to one another. So his hypothesis in one of the papers was that these mechanisms were not only there separate to each other, but also complementary. So they work together to produce stable and efficient gait. So that's our parameter, or those are our parameters of dynamic balance control. And what we wanted to know is, does a changing environment induce changes in dynamic balance control? So we hypothesized that this dynamic balance control is adaptive, that we need adaptation or adaptive behavior to remain stable. But can we actually measure this? And to do this, we used a split belt treadmill, which you see in the videos over here. So as you can see, there's a gap in between the two belts, and our participants are basically walking on two treadmills. We can control the speed of these two belts independently. So we can set the speed of one belt to 2 or 3 times higher than the other belt. And that's exactly what we'll do. So we get our healthy young adults and we let them walk with the left belt at 3 times the speed of the right belt. And as you can see, our participant is struggling a bit and it doesn't look quite that comfortable. And what I'd like you to focus on, or what's an often reported parameter in these studies, is that there's an asymmetry in step length. So what you can see is that with the left foot, our participant steps next to the right foot and doesn't even make a full step. With the right foot, the participant produces a longer step. Now, the amazing thing is that with this weird task, and our participants have never done this before, know nothing about these treadmills, in just 10 minutes, without any instruction, humans can adapt to this task. So without any training, no instruction, they adapt their walking behavior. At least it seems a lot smoother. And we see that there's now an adaptation of step length. So I'll go back to the video. There we go. So you can now see that the participant places her left foot in front of the right foot, and it looks a lot, relaxed, and the step lengths are more symmetric. So this is our paradigm to study the adaptive behavior of humans in a very controlled way in our lab setting on a treadmill. And like I said, there was adaptation of step length. So if we take our measure of step length asymmetry, which is a normalized measure, so we take the difference between the left and right step length divided by the sum, which means that if the value is 0, the left and right step length are equal. If it's negative, the left step is shorter than the right step, and if it's positive, the right step is shorter than the left step. And what you see here in our group average values is that at the beginning, so the first adaptive behavior, at the very first, there's a value around 0. That's our baseline measurement during normal walking. And then we start the split belt mode, and the step length asymmetry goes down. It becomes very negative. And over this course of 10 minutes, our participants, our healthy young adults, adapt their step lengths towards and even over an asymmetry value of 0. So that's interesting. We already kind of knew this from previous studies. And we were wondering, is there also adaptation of balance in this context? So do we indeed adapt our balance parameters to walking on a split belt treadmill? And the easy answer is yes, balance control is adaptive. So we took our margin of stability. The first two parts on the left, right here, show margin of stability as slow the other way around, fast and slower walking. And then we have this long line where we see a black line and a red line. The black line shows our margin of stability of the leg on the faster belt, and the red line on the slower belt. And we see that it increases a lot at first, and over time also adapts. And there's an asymmetry, but I'll get back to that in a second. Now we had our other measure, the mediolateral foot roll-off, and we see that the opposite happened here. So if you look at this longer piece again, we see that there's a negative foot roll-off, which means that participants rolled off their foot inwards. So they had a large margin of stability at first, and they rolled off their foot, they inverted their foot during stance, possibly to correct for this very large margin of stability. But as their margin of stability became smaller over that course of 10 minutes, they started to roll off their foot more outwards. So those are the separate measures. And we were wondering if these measures or these mechanisms are complementary. And that is indeed what we found. So we found that when there was a higher margin of stability at the bottom left, or the left or the right of the axis, there was a more inward foot roll-off. So people directed their center of pressure more inward. And if they came to a value near 0, they would have a more outward roll-off of the foot. Even more so, if we look at the blue ellipses here, those represent the early adaptation phase of split belt walking. So this was at the beginning when they were learning the task. They show a high margin of stability with a lot of inward foot roll-off, and they adapt this complementary mechanism towards a margin of stability closer to 0 with a more outward foot roll-off. So those were our initial findings, first findings with regard to adaptive control of dynamic balance. But there's something that we were wondering. Two things actually. Like I said, the values here were asymmetric. So we saw that there was a very much larger margin of stability, larger margin between this extrapolated center of mass and base of support on the fast belt than on the slow belt, which caught our surprise a bit. And there was a margin of stability of 5 centimeters. And this is something we didn't see in any of the normal walking tasks, neither did we see it in any patient groups. And since these were healthy young adults, we wondered, well, is this actually necessary for stable gait, or are we looking at something else? So we went back into the underlying equation of the margin of stability plotted below. And you can see that the margin of stability, which is here the value B, depends on the step width, which is W, and stance time, which is T. So there's a relationship between the margin of stability and stance time. However, based on this equation, as originally presented by Huff, we wouldn't be able to explain this asymmetric behavior. So why did they have a higher margin of stability on this fast belt than on the slow belt? And with a bit of help from Huff, we were able to rephrase these equations and make them dependent on both a left and right stance time. So we thought, our hypothesis was that there was a dependency of the margin of stability on both stance times, so on the left and the right leg. And if we have this equation, we can very easily input the step width that we measure and the stance times that we measure on our treadmill to see whether our predictions are right. And to put it very simply, They were quite good. There's a small offset, so we see our measured values in black and in red, and we see our predicted values based on these new equations in yellow and in blue. There's a small offset, but we can see that these local fluctuations over time were predicted quite accurately, with which we concluded that the margins of stability depend on a combination of step width and bilateral single support times. Now you could look at this and say, well, were we actually measuring dynamic balance then? Or is this margin of stability, this value, this parameter we focused on for a couple of years, just a simple addition of step width and stance time, and it might not have anything to do with balance. And that brought us to the final conclusion of this part. It's that in the case of split belt walking, you might indeed wonder that. So the margin of stability of 5 centimeters is ridiculously high, and there might be other processes going on, such as optimization of other asymmetries or the optimization of metabolic cost. However, if we apply this theory to people, to clinical populations, we see that they exploit these passive dynamics for their benefit. So in people with a prosthesis, we know that, people with an above knee prosthesis who have no mediolateral ankle control due to the prosthesis, we see that they have a larger prosthetic margin of stability, because they are not able to apply this mediolateral foot roll-off that we studied, and thereby they can safeguard it. And they gain this margin of stability by changing their stance times. Similar in stroke, we see that they often have a shorter paretic stance time, by which they increase their paretic margin of stability. So with these simple relationships, we're actually able to explain some of the behavior we see in these clinical populations. And then we decided to turn the tables a bit. So we did conclude that balance control was adaptive during human walking. But if we then look at the assistive devices that are used in clinical practice, or even the simple strategies that are used, very often they provide balance support. So we have a simple walking stick or a very advanced exoskeleton. They often provide you support during gait training, and they take away the balance problem. And even without these devices, if you have a physiotherapist supporting the patient, they're basically holding them up and making sure that controlling the balance is no longer a problem. But if this balance control is so adaptive and plays such a large role in walking, then what happens to motor learning when you take this balance control problem away? And for this, we used a part of the split belt paradigm that I hadn't mentioned yet. Those are the after effects. So after our healthy young adults walk on the treadmill for 10 minutes, so they have adapted to this split belt state, we set the belts at equal speeds again. And then you get a fascinating phenomenon. It's where there are very clear after effects of walking in the split belt mode. For the participants, this is quite shocking. Luckily for them, it fades away in about 2-3 minutes and they go home all safe and normal. They are quite shocked, and it's really hard for them. You can see in the first 2 steps, their leg basically blocks and doesn't want to go into the swing phase. Now, in adaptation literature, these after effects are sometimes described as an indicator of motor learning. They say that something has changed or been recalibrated in the control of walking, and something has been learned. So we use these after effects as a paradigm for learning. And we studied whether external support affects locomotor learning. And very simply, we did that by holding on to the handrails during this split belt walking task. We used the step length asymmetry again as our measure of learning, and we measured 3 experimental groups. Actually, we measured 5, but I've put 3 in the presentation. First of all, we have our control group. That's the group you just saw. They weren't allowed to hold on to handrails. Then we had a group who held on to handrails on the side of the treadmill throughout the whole experiment. And finally, we had a switch group. They held on to the handrails during baseline and during split belt walking. But at the end of the split belt walking, at the end of the 10 minutes, we counted down from 3 to 1. They had to let go of the handrails at the exact moment we went into tight belt mode again. And this was to check whether any potential effects during this after effect. So say we wouldn't see after effects in this handrail group, then you could always say, well, they don't have after effects because they can still hold on to the handrail. And we want to make sure whether or not they have learned anything. So if they would have to let go of the handrail at that point, they wouldn't be stabilized anymore. And if we would see after effects, they've learned something. If we wouldn't see after effects, they wouldn't have learned anything. I'll show you that in the video as well. So we had our control group, you've seen that. And then we have our handrail group and switch group, who at this point behave quite similar. And as you can see, the participants that were allowed to hold on to these handrails really made use of it. You can see them lifting themselves up a bit. These are healthy young adults. They have the power to lift themselves up from the treadmill. And you can also see that they struggle with this task a lot less. It's clear from the video already. Low system resources. All right. Well, let's try it. Seems the computer is struggling a bit.
With all the videos you have on, I guess.
That's too bad. Yeah. I'm going to give it a try anyway. So we have our After Effects. We can see our control group struggling. Maybe if I then put this one on pause, it'll be a bit better. Get rid of this. But we can see in our handrail group that there are, well, there might be small after effects, but definitely not as much as in the control group. And then most importantly, we have our switch group. Oops. So it'll replay in a sec. You can see that this particular participant was a bit hesitant to let go of the handrails. And the first step is a bit hesitant, but the after effects don't seem quite as big as in the control group. Based on video data, this is a bit hard to assess. So we'll go on to the actual data. We've seen this before, right up to here. And now we have our after effects. So in any classic adaptation paradigm, we see after effects in the opposite direction. And here we do as well. So they first had a negative asymmetry during adaptation, and now they have a positive asymmetry, and they go back to baseline behavior in 1 or 2 minutes. Now, if we look at our handrail group, we can see that indeed, at the beginning of adaptation right here, they were not quite as perturbed by the split belt walking mode. They even ended at a bit of a higher level of step-length asymmetry, more positive. And during the washout phase, so back in tight belt mode, they didn't show quite as much after effects, which is what we hypothesized. But like I said, at this point, they were still supported. So it could be due to the support. Therefore, we had our switch group, which just like in the video, in the very first step, may have shown some small after effects, but in a matter of, I think based on this, it's 10 seconds, they were back to baseline behavior. So the difference between this green and black line, the switch group and the control group, was quite surprising to us. So with that, based on these results in this context, we concluded that external support reduces locomotor learning, which is also in line with some of the upper limb visual motor rotation studies we know. And we think that's due to a reduced challenge for balance control. So the task has become easier. You don't have to think about how you control your balance anymore. And adaptive control of balance or balance control is a very important part of learning to walk. To apply this a little bit, without making very definitive statements, because these are all healthy adults, in clinical practice, you might want to wonder what kind of support you offer to a patient at which level. So should you use a safety harness instead of handrails if they are able to mobilize themselves? Let's see. With that, we came up with, well, a whole framework of step width and stance times affecting margins of stability. And we also had some conclusions about the anterior-posterior directions. And with that, we did a couple of studies to apply this very simple model still to gain some knowledge about clinical populations. So why are some clinical populations walking quite abnormally? We did a study with James Finley at USC, at the locomotor control lab, where we studied walking after stroke. We got talking with James. He was doing a lot of stroke research, and we both had these hypotheses about, or well, we saw a phenomenon in literature in several studies using margins of stability, where we saw that, I'm going to pause this for a second, where we saw that margins of stability might be covariated. So up to now, we've only focused on the mediolateral margins of stability, but you can also describe this in the anteroposterior direction. And we saw that often when one increased, the other decreased, especially in clinical populations. So we investigate this in reactive stepping post-stroke with all the knowledge that we now had of these balance mechanisms. So there's a short video here, and the hard thing is we only need very small disturbances on the treadmill, so small acceleration of deceleration to perturb our participants. So it's not quite visible, but when the video plays again, the first two steps are normal. And then now comes the perturbation. You can see the participant responding. I've tried in the full resolution video, but it's not possible to see the belt moving. It's these very small perturbations by which they're off balance already. So we use this to study whether there was a covariation in sagittal and frontal plane balance control based on these margins of stability. First of all, we found that they were asymmetric. So that's what I said before. People post-stroke stand on the paretic leg, their affected leg, for a shorter time, by which they have a larger margin of stability on that side, which they could use to safeguard their balance, perhaps. And indeed, we found this hypothesized paretic coupling, and only in the paretic leg, which means that if, in this case, they were perturbed in the sagittal plane, if they responded by making a larger step, they had problems with making an outward step. And we didn't see this at baseline stepping. We didn't see this in the non-paretic leg. And we also don't see this in healthy adults. And this helps us to know where to look in stroke patients. So we often see that they have some coupling in muscle activations, or this has been described in terms of joint torques. And it seems that in the paretic leg, this is the cause for some of these balance problems. So with this, we know, based on these simple models, we know a little bit. And from here, we have to further study what's behind this weird coupling between the sagittal and frontal plane balance control mechanisms. Given the time, I'm going to skip that one. I can go back to it after if you want. There was another example in Parkinson's disease, but the idea is quite the same. So this shows how, based on a simple model still, the inverted pendulum model, we can gain a lot of knowledge about how people walk and why they walk, and perhaps how we can improve it. But there was a problem. We had this inconclusive results about people post-stroke in the lab at USC, and it was very hard to pinpoint a concrete reason to it. In people post-stroke, there are a lot of things going on simultaneously. And that's what we focused on in my postdoc project at KU Leuven. So that's the next part. This project is the SimStroke project. And here we move from simple to a way more complex model. Because here we use simulations of human movement. And I'll elaborate on that a little bit in a second. Basically, with simulations, we can simulate what we cannot measure. So for instance, I was just talking to Sjoerd. You can it would be hard to paralyze someone experimentally, would be maybe a bit unethical, but with a simulation, we could do something like that. So in a computer model. So in this project, we focus on walking after stroke. And the problem here is that people post-stroke have a lot of underlying impairments. They have problems with motor control, muscle control, sensory function. And in research, it's hard to pinpoint what the effect of an impairment is on a gait pattern. These groups are so heterogeneous that in studies, often the effects cancel out each other, and it's hard to distinguish what causes what. But with predictive simulations, so full computer simulations, we're able to assess isolated effects and interaction, or to put it a bit more popular, we can answer what-if questions. So what if we increase plantar flexor power in a stroke patient? What if, how would that influence the walking pattern? Well, if we would do this experimentally, we'd have to take 30 stroke patients, train just their plantar flexor power, then publish the paper, and the review would say, yeah, but now you didn't only train the strength, you've also trained coordination. So we're still inconclusive about what happened. But with simulations, we can say, well, we'll just up the power from the plantar flexors and identify a causal relationship between plantar flexor power and walking. Even further so, if we apply this, we can develop personalized predictions for patients, and for each individual patient, pinpoint what their what underlying mechanism or underlying deficit, causes their walking problems. So for patient A and patient B, who walk quite similar, it could be that for patient A, spasticity causes the problems, whereas patient B has problems with muscle weakness. This could help us to identify training targets, but also design assistive devices. So how does this work? First of all, so like I said, we have a more complex model. We have a neuromusculoskeletal model, which is a mathematical description of the neuromuscular system. Oops, a bit too far. So to go through it quickly, our model produces muscle excitations through muscle dynamics, muscle forces, while the sensory information is fed back into the system. So there's a loop there. Based on the musculoskeletal geometry, it produces joint torques, and together with the external forces, we get our skeletal dynamics and movement. Now in this model, there are a couple of terms in red, and these are the parameters that we can personalize to the individual patient. For instance, we change the muscle tendon parameters. We can implement this model of spasticity. We want to implement sensory function, and we have a model of motor control in there. So if motor control is impaired, we can model that as well. By manipulating these parameters, we can elicit these causal relationships. Now, the goal based on this model is to simulate a walking motion. And we do that within an optimal control framework, which means that we have the assumption that movement is optimal in some way. And the goal of this optimization process is to minimize an objective function. And I'll elaborate on that objective function in a second. And to go a bit technical, we use direct collocation to do that. Now, the inputs into our framework are this OpenSim model with 31 degrees of freedom and 92 muscles. It's a 3D model, in that sense, quite exciting. We impose periodicity. We want to simulate a walking motion. And to do that, we say, well, the beginning and the end of the motion have to be the same. That way we can basically copy paste it after each other and get a continuous walking motion. We impose an average walking speed, so we tell it to how fast to walk. And we have a cost function, which is shown here, but I now realize it's very small. It consists of metabolic energy rate, muscle activity, joint accelerations, passive torques, and arm excitations. Now, the arm excitations are mentioned separately because we don't have muscles for them in the model. So they are torque actuated. Otherwise, they would have fit in with the muscle activity. Importantly, no experimental gait data goes into this model. So this is a pure mathematical description, and it comes up with its own solution that, according to these calculations, are optimal. The outputs are the walking mechanics and energetics. And then within 30 to 60 minutes on a standard laptop, we can produce this walking motion. So like I said, there's no experimental data in there, but the resulting walking motion is quite realistic, which is exciting because now we can actually use it to study walking. So yeah, I can go into this very quickly to give an idea what's needed for this project. We have to collect experimental data. We include stroke subjects, some basic characteristics. They're chronic stroke patients and they have to be quite mobile. And we collect basically a lot, 3D kinematics, 24 muscles EMG, and ground reaction forces during a whole bunch of tasks. First of all, for our model personalization, we estimate muscle tendon properties based on some functional tasks. So imagine squat movements, a sit-to stance, and passive range of motion on the bench. We assess reduced selective motor control based on a clinical scale. We estimate sensory function based on joint position matching and a sensory organization test, which is, I think, still some of the most complex data. So if anyone's got a good idea how to quantify sensory function in stroke patients, please tell me. We measure spasticity. We quantify spasticity with the IPSA test, which was developed. And during all this, we measure the kinematics, EMG, and forces where we have a force plate. So from all these tests, even if the clinical tests, we have all the quantitative data. Then we have our assessments of dynamic balance control, and these are to validate our model. So everything we do here is not input into the model, but we check whether what we measured and what we produce with our simulations is similar. Now, I believe this is you, Shoot.
Oh, yeah, it seems like it, yeah. Long time ago in Leuven.
Long time ago. So that's our Karen platform. We do this, right, isn't it?
It is,
yeah,
I think,
yeah.
The installation of the
I've got the high-res Melvin, if you want. So we measured standing balance. We do, in the future, we want to do some standing balance simulations as well. We assess walking balance with treadmill belt perturbations. And like I said, we use these to validate our model predictions. So that's all ongoing right now. But to give you an idea of what you could do with this framework, so this project is still running, I'll give you an idea of a study we're doing on isolated muscle weakness. So a very hot topic in walking after stroke is that people post-stroke often have a step asymmetry. Basically, there's two lines of thought there. There's the people who say this asymmetry doesn't matter, it's there, it's the result, and we shouldn't focus on it on training. And then there's a group who very strongly said this asymmetry you should take away. If you take it away, the walking will get better, the balance will get better. It's a bit of a cause-effect problem. But experimentally, there's once again a large heterogeneity in impairments underlying this asymmetry. But with predictive simulations, we can study the isolated effects underlying this asymmetry. And in this case, we focus on muscle weakness. So we take our simulation framework, we take a generic model. So this is not personalized to a patient. We have like a healthy model, which in real life is actually Friedel-Legoten. In case anyone is wondering, we weaken the muscles of 6 muscle groups that are important for walking, and we do that unilaterally. So we have how do you say it, a modeled hemiparesis. And we weaken the hip, knee, and ankle flexors and extensors, so one by one. And then, of course, we did one control simulation without weakness. On top of that, so we let those models walk, and I'll show you that in a second. We impose step length symmetry to be able to test this line of thought that says, well, you have to get rid of this symmetry. Even though it's there, you have to train on it and get rid of this step length asymmetry when people post-stroke walk. So whenever a resulting simulation had an asymmetry higher than 0.03, we put a computational bound on the step length. So we have to do everything. We have to mathematically say, well, the step lengths have to be equal, and see what came out there. And we imposed an asymmetry on the control simulation as a check. And then our outcome measures in this case were just resulting step length asymmetry and the cost of transport. And to show you, the video in the back, the skeleton in the back is our control simulation. And in the front, you see a model of weakened plantar flexors, which have a very clear effect on the push-up. So you can see that by weakening the plantar flexors, our model predicts that there's a shorter step after paretic push-up than after non-paretic push-up. Or another example, if we weaken the hip flexors, you get this very clear effect on the weakened side. So given the time to go through this, so what we found was that indeed, after unilateral muscle weakness, there is asymmetric walking, but it's not quite that simple. Our main findings were that the asymmetry is dependent on the muscle group and the gait speed. Especially weakness of the more distal muscles cause the most step length asymmetry. So we see our step length asymmetry here. And the more further along we go, here are the more proximal muscles, and here are the plantar flexors and dorsiflexors. And we see that weakening of those muscles causes most asymmetry. Furthermore, we tried 2 gait speeds, walking at 0.8 and 1.3 meters per second. And the asymmetry in the more proximal muscles depended on the gait speed. So these are still some preliminary results. We're going to do a lot more on this. But actually, this was quite exciting because this allows us to get into some of this heterogeneity that we see in step length asymmetry after stroke. And maybe we'll be able to pinpoint some of that. On top of that, there's this thought that you have to get rid of it and that people post-stroke will walk easier if you get rid of walking with a more symmetrical step length. But what we saw is that in all of the weakened simulations, the metabolic cost of transport was higher, and reducing asymmetry by putting these computational bounds on the model never reduced the cost of transport. Now, future research would definitely want to do some things on top of that. So putting gait stability, and you can interact with other impairments such as the spasticity and other parameters that I mentioned. How long ago? Yeah.
10 minutes.
Oh, okay.
Then there's room for questions.
Yeah,
so we have 20 minutes left. So if you do 10 minutes more, then we have 10 minutes.
Yeah, that should be right. Yeah. Yeah, I'm getting near the end of it. So I started at the simple inverted pendulum model, and then we made a switch to this way more complex predictive simulations with all kinds of factors in it. But the funny thing is that sometimes these complex models rely on very simple relationship, or a complex model relies on a simple model. And we had a problem because we want a model of coordination, of motor control or muscle coordination. And we didn't find anything that was proper for stroke. So we want to model the reduced coordination that people post-stroke have, but we weren't quite satisfied with the things that were available in literature or that we published ourselves, to be honest. The basic instinct that we had was to go to muscle synergies, which have been described in literature in a huge variety of forms. The problem there is that if you impose synergies, so if you say, well, these muscles all have to be active together in such a simulation framework, you're imposing not only the neural constraints due to the stroke, but you're also imposing task constraints. Some muscles are simply active together because they have to be when you want to produce a walking motion. And we don't want to input those task constraints because we also don't want to input gait data. We want a fully predictive model. So we're looking for something that describes only the neural constraints. And then the solution, or at least we're trying that right now, was very simple co-activation patterns. So our hypothesis was that if we ask people post-stroke to make, for instance, a very simple knee flexion extension movement, and we would identify co-activation between two muscles during that movement, and then we'd identify the co-activation during their walking motion for the same muscles. If there'd be high co-activation during this movement for a participant, and there'd be high co-activation during walking as well, and there'd be a correlation across the group, this would distinguish a neural constraint. So if someone has high co-activation between two muscles during simple knee flexion extension and still show it during walking, then it must be really hardwired. But if they don't show the co-activation during this very simple task, but only during walking, then it might very well be a task constraint that we're looking at. And there's a lot of data in there, so I'm just going to plot it all at once because this is the last data I have. We tried a bunch of muscle pairs based on what we found previously in literature, because with all the muscles you end up with a huge amount, so we have to make some choices there. And what we found was that for two muscle pairs, it was the vastus lateralis and gastrocnemius medialis and the rectus femoris and semitendinosus pairs, we found that there was a correlation on group level between co-activation during this isolated knee flexion extension movement and walking. To give you an idea of what that looks like, if you look on the top, you see on the top left here, someone with high co-activation during the knee movement, and someone here with low co-activation during this knee movement, to illustrate a bit what this looks like. And it seems as if for part, they cannot activate one muscle without the other. So the preliminary conclusion there was that with instrumented assessment of selective control, because this is one of those clinical skills that we measured instrumented, we might be able to identify these neural constraints, distinguish them from task constraints, and we could use that as an input to our model. So this is a very simple correlation, which we can then use as an input to our complex simulation framework. Yeah, I think that brings me to the end of the part of the simulations of walking balance. So then we have the whole spectrum of simple to complex. And to wrap that up a bit and see why I said from simple to complex and back again, we're still working on the predictive simulation project. Like you can see, there was a lot of preliminary stuff on that, so there's definitely more coming. But I'm also going back to the simple models again. We're currently doing a study on very slow walking. It's for our participants the most boring study so far. They have to walk at 0.1 meters per second, which is awfully slow. And we measure the whole spectrum to 1.4. And we're trying to look at which points these inverted pendulum models are still valid, because we take some data from healthy subjects at a high walking speed. We say, well, the inverted pendulum model works. We apply all that to the patients, but some of our patients walk at only 0.3 meters per second, and we actually have no clue whether our models are still valid. So we're moving back from simple to complex and moving back in between. And what I'm thinking about, and you're definitely open to discuss it with me, is some idea of generalization of balance strategies. So I've shortly touched upon that, but I think if we want to get a better comprehension, a better understanding of how balance is controlled, we have to get an understanding of how these strategies show themselves across environments, tasks, and populations, and other specific thing for every specific situation. And I want to do that, of course, by a combination of experiments and simulations. And that's it. Thank you.
Thanks, Tom. So there's room for questions. No one? Yeah, nothing.
So I have a question about the step length asymmetry series and simulations. Obviously, it's quite easy to walk with symmetric steps, but still walk very asymmetric.
Yeah.
Right.
Yeah.
So how does that pin out into these simulations? So you say, okay, I force a symmetric step length.
Yeah.
But does that then lead also to a symmetric front progression over a gate side, like forward replacement relative to the front, or do you see that these asymmetries increase but are counter in direction, which makes up then symmetric step?
Yeah. No, so we can do two things there. If we want to do a very fast simulation, we actually only simulate half a gate cycle, then flip it, and then you get a symmetric movement. So that's one thing. We don't do that because otherwise you couldn't get the asymmetric movements. So in the weekend model, if we enforce these asymmetric step lengths, there are definitely asymmetries elsewhere. And very simply within this study, we're also focusing on stance time, but that's also because a lot of experimental work has focused on those parameters. If you look at trunk kinematics, for instance, or other kinematics or muscle activations, there's a lot of asymmetry going on to achieve asymmetry in some parameter, which makes you wonder why you should even focus on that.
Yeah, so maybe you need more control parameters than just step length asymmetry.
To produce a very symmetric movement.
Yeah.
So the problem, so if in a weakened model, so say we have hip flexor weakness, and we say, well, we want everything symmetric, it might become, so aesthetically that would look nice, right? If we have a patient and it would look great, they go up in the crowd. In simulations, that could get a bit troublesome because the more constraints we impose, the stiffer the problem gets, the larger the chance it doesn't even converge. But it's definitely true. So we're only imposing one thing. We're also doing a combination with stance time. And the reason we choose this is because this is often what's also focused on in a lot of experimental studies and clinical practice. But it is very much focused on that single parameter. The cool thing is, and that's what I think is most clear from these videos, is that if you weaken some part or you impose spasticity, you sometimes get these compensation patterns as a result of your simulation. And that helps you to understand why patients walk the way they do. So I think it's very cool that within developing these simulations, we run into something that we call compensation, but apparently it's also the most optimal given the cost function that we use. Yeah.
More questions, Dino.
Hi, thanks for your nice presentation. It was very interesting. To follow up on Melvin's question, so with optimization criteria, it uses 4 or 5 different terms, probably different ratings. Whether the same for the healthy versus non-healthy patient, and second, would you check how sensitive the outcome was?
So in this case, we always use the same weighting. So there are 5 terms indeed. Some of them are weighted a lot higher. Basically, it's a combination of metabolic cost and muscle excitations. And then there, for instance, there's a term in there for joint accelerations. If we get rid of that term, the movement is not at all smooth. So some of these terms are in there for a different reason. The weightings were determined in a previous study, so we always keep them the same. And then it was validated against an experimental data set. Now, so that's based on one study. So there was, you could look at it as a case study. So we have an experimental data set. We modeled our OpenSim model based on dispersion. And then we go for the weightings due to which the movements match. Now, the thing we'll have to do once we get to the stroke data, so once we do the case studies in people post-stroke, is look whether our weightings are still correct. And then indeed we'll have to check the sensitivity to all these different weightings. And if we have to change the weightings, we have to rethink what they actually mean. So why do we have to change some of these weightings for patients, for instance? But that's all to do work. Yeah.
Well, we also like sort of stress many times that in no way.
Yeah.
But you sort of did that implicitly by tuning many parameters there are and optimizations such that the model will be walking sort of the same.
Yeah, I think.
So it's sort of implicit you actually did.
Yeah. So in part you're right there. I think the main thing I was trying to say there is we did not. It's not a tracking simulation, for instance. That's the main distinction. But and that's a debate we often have is how much can you impose before you indeed are implicitly imposing the whole walking motion. So there's a trade-off there. Yeah. What we're looking for in the end is not tuning the weightings of the cost function for every separate patient. But if you think that this is a correct way to simulate a walking motion, then you're looking for a global solution in which, for instance, you do tune the muscle tendon parameters because we think that those are specific to the patient. So you tune some parameters, but for instance, the cost function you should be able to keep that the same across different patients or different groups. But there's a lot of work to do there still. Yeah. Yeah.
More questions? Nelson again?
Yeah.
Okay, yeah, sure, go ahead.
Yeah, so you said you were surprised by the very large margin of stability in the first part of the presentation. I was sort of surprised myself as well, although I've read, of course, your entire thesis, for which you got the thesis presentation right, but still, couldn't it be simply an effect of the treadmill setup? So you have the split belt that basically enforce you to walk with a wider step.
Yeah.
And couldn't it just be an artifact of that, given that also step weight is part of the equation?
Yeah. So I think there's more. Is she gone? Oh, there. Sorry. Yeah. So I think Moira already showed that at the ISPGR conference very nicely. The effect between the split belt treadmill and the CMOS, so it's something we already thought, all of us, for a long time. However, I do think that's more of we call it a flooring effect. So you can't go smaller than that, but that wouldn't explain why they go as high as 5 centimeters. So I do think there's a bit of a confounding factor there. People might have normally maybe walked narrower, but then it wouldn't explain why they go up to 5 centimeters. Or am I? Yeah. Yeah. Yeah.
More questions? Well, I have one related to this. So you seem to interpret the fact that people have a larger margin of stability as being more stable. Now, there is a problem with that because most pathologies actually walk with a larger margin of stability.
Yeah.
And I'm saying that people with most pathologies actually walk, and I'm not looking at Dina here, but more stable. Dina has a problem with the use of more stable. So.
Okay. Yeah.
So are you suggesting that?
No, no, and it's a difficult point, and it's also a bit of a problem with this margin of stability, or at least the interpretation of it. What I think is the case that mechanically, if you walk with a larger margin of stability, you could be more robust against the perturbation in that direction. However, these patient groups are clearly less stable, or at least they fall more. I'm gonna be careful. I know where this. Choose my words very carefully here. No, so that's difficult. I think the margin of stability is not a one-on-one mapping of stability. You could say the stability is either falling or not, and during these experiments, no one fell, so they were all stable. So it gives you some idea of where they place their feet with respect to the center of mass or extrapolated center of mass, but it needs further thought to understand why they walk that way. But you cannot say, well, they walk with a larger margin of stability, so they're more stable. You could claim quite the opposite, say, well, they might feel unstable, so for safety walk with a larger margin of stability. But it always needs a further discussion, which is a bit of the problem with this measure. Yeah.
Okay, if there's no more questions, then unfortunately there's no drinks outside because the students are all at the Lustum. But for those who want, we can join me with the speaker to the basket after this. And I'll thank you one last time, Tom. Thanks for being here.
Thank you.
Leuk werk.